So what we're going to look at in chapter 4 is going to be a little bit of some balancing and some stoichiometry kind of calculations. And what we're going to do is use this for some of the labs we have coming up in the future, which is an aspirin lab where we're going to make some aspirin. So first thing I want to talk about is the difference between empirical and molecular formulas. So I've given you a couple organic molecules here with their corresponding names. And so when you look at a formula with carbon, hydrogen, and oxygen, is there a way that you could reduce it further? So if I see glucose is C6H12O6, I could reduce each one of these by 6. So I could get CH2O. So the smallest combination there is going to be what we call your empirical formula. While some factor, in this case it is a factor of 6, is multiplied, or multiply your empirical formula by that factor, get to your molecular formula. So molecular formula is how it exists in nature, meaning if I see C6H12O6, that is the formula of glucose. Maybe CH2O does exist, maybe it doesn't, but this is the relationship between molecular and empirical. So if I look at sucrose here, it is C12H22O11. There's no number I could really do to reduce that further. So it actually is the both the empirical and the molecular, so you could write both next to it to kind of point that out to yourself. If I look at caffeine, C8H10N4O2 can be broken down by dividing by 2 to C4H5N2O. If I look at formaldehyde, CH2O, I really can't break that down. So this is both the empirical and the molecular formula. Vitamin C, C6H6O6 can be divided by 2. So I have C3H4O3 for the empirical formula. That is vitamin C's formula. And then benzene. Well, benzene, I could reduce it down to CH, but really this is the molecular formula is going to be something we look at in the near future. It is a very unique molecule. It is 6 carbons in a ring, and it actually has some double bonds through the structure. That gives you hydrogens on each one of those carbons. So it's a very unique molecule that we're going to be talking about in the future. So we're going to use these carbon molecules, and we are going to do some what we call balancing of chemical reactions. So remember, balancing, what you're doing is putting a coefficient in front of a formula. You're not changing the formula. And we are going to focus on combustion only, and that is because combustion reactions involve a carbon molecule, and then you're burning in an oxygen to produce carbon dioxide and water, and you always have the same products. But we're going to be using this kind of as a model for our aspirin lab, that we're going to be computing how much aspirin should we make from a starting material. Excuse me. So I'm going to show you how to balance, and if you know how to balance, you could just skip this part of the video, as that's all I'm going to be talking about. But what we're going to do is look at how many carbons, hydrogen, and oxygens are on each side. And I am going to go in this order, and there's going to be an easy way for you to remember that. So I have 4 carbons, I have 8 hydrogens, and I have a total of 4 oxygens. Excuse me. Over here I have 1 carbon, 2 hydrogens, and 3 oxygens. So if you look at 1, 2, 3, that's an easy way for you to remember. I'm going to balance carbon first, then hydrogen, then oxygen. Well, why do I have to do that? Well, if I look at my products, CO2 and water, this is the only place carbon can go, and this is the only place hydrogen can go, but oxygen goes for both. So if I put a coefficient, it's going to change how many oxygens are there. So that's why I want to wait for oxygen till the very end. At the very end of my balancing. Other thing is, oxygen is sometimes all by itself over here, so just changing one thing. Now this one is unique because I do have oxygen in that molecule. So I am going to have to look at that as well. So let's start with carbon. So I need 4, so I put a 4 as a coefficient. I'm not going to recount my oxygen till the very end because I don't need to worry about that. I need 8 hydrogen over here, so I'm going to put a 4 in front of that to get me my 8. And then I count my oxygen. So I have 4 times 2, that is 8, plus another 4, that is going to be 12. Okay, so I think, all right, I got to put a 6 in front of that O2, but unfortunately I do have an oxygen in that carbon molecule. So what I like to do is take the total number and then subtract how many oxygens are in the carbon molecule. So I know that I need 10 oxygens to come from here. So what number multiplied by 2 is going to give me 10? That's going to give me the number 5. So that's the balanced chemical equation. So I literally call this a 1, that's a 5, a 4, and a 4. So to your next page, if you would take a moment and see if you could balance this next problem. Again, balance carbon first, then hydrogen, then oxygen. So pause the video if you need to and see if you can balance it. All right, so you should have ended up with the 12 in front of the O2, a 12 in front of the CO2, and 11 in front of the water. So the last thing I want to show you with the balancing is what if you get an odd number? And you can't really identify these necessarily as to when they are going to be this problem. And how I do this is my own personal way of doing it. So if you don't like this, then you could kind of ignore me and do your own thing. So in this problem, I'll just make it a little bigger here. I have 3 carbons that I need to put over here, so I'm going to put a 3 there. And then I have 8 hydrogens, so I'm going to put a 4 there. Okay. Now I'm going to count my oxygen, so 3 times 2 is 6, plus 4 is 10. So I'm thinking, oh, I have an even number, that's pretty nice. But I do have 1 oxygen in that carbon molecule. So I'm going to take 10 minus 1 is going to give me 9. So I need 9 oxygens overall. So I can't really do that with the 2. So what I'm going to do is put a 9 halves in front of that, kind of let myself know that I need about a half of oxygens in there in order for it to work. Because if I multiply this by 2, I end up with 9. But I don't want to leave it in the fraction form. So what I'm going to do is multiply everything by 2, and that will get me to my correct balancing. So I'm going to put a 2 there, put a 9 there, make that a 6, and make that an 8. So my correct balancing is a 2, a 9, a 6, and an 8. So that's what I do. Again, if you just recognize that this is an odd number, you could just put the 9 in front of it and then double everything else. That would be a way to do it. So again, pause the video and see if you can balance this one. Again, this one comes out to be an odd number. So you should have ended up with the 2, a 13, an 8, and a 10. Again, once you get that odd number, you should just stop yourself and go, okay, that's where the odd number goes, and then double everything. But don't forget to double, especially the CO2 in the water. That's the common mistake that you see. So that's all we're going to do with balancing. That's all we're going to do with balancing.